So, hi everyone, I'm Rong-Hao from TU Eindhoven. I'm gonna introduce RFIMatch, a system for distributed batteryless near-field identification. This is a scalable ID solution for embedded and wearable applications. This is a joint work between TU Eindhoven and National Taiwan University, and thanks for Stephanie's introduction. First of all, let's talk about RFID. It's a reliable technology for near-field identification. RFID has many applications, such as everyday transactions and payment. RFID tags are battery-free, maintenance-free, so they have been deployed at scale. However, RFID readers are not deployed at the same scale. People often wait in line to get their tag identified. The readers cannot be deployed at a larger scale because they need to be powered. The power requirement of an RFID reader increases the hardware and maintenance costs, and therefore makes it practical to deploy at a larger scale. So we are motivated to think about batteryless RFID reader, which can be a solution for scalable deployment. In doing so, a tag could have more access points, even get localized. Furthermore, each reader can pair with another reader, just like those NFC phones. Having distributed batteryless readers can enable a range of RFID interaction design. Well, actually, it's not a terribly new idea. Previous work has realized the same function using the same infrastructure. They use an ultra-high frequency reader and the tags. A single reader can detect multiple tags within its sensing range, for instance, 30 square meter. The reader powers up the tags wirelessly using an antenna, and the tags transfer their ID information to the reader. The presence of more than 100 tags can be tracked simultaneously. If we make a move to turn two tags off at the same time, the reader will capture a correlated state change event that indicates the pair identification of these two tags. From a user's point of view, the tag functions like a batteryless tag reader. To trigger correlated state change, RFID applies copper tape with each tag. When one stacks on another, which is the counterpart, the stacking turns two tags off at the same time. In this example, the checkerboard has 9 batteryless readers. In this year Chi, we present RFID bricks, which further allows for stacking in 4 orientations and Z-axis. We modified the tags using magnetic connectors. When one stacked on another, it turns 2 tags on at the same time. The magnets will force the alignment. In this example, every block is a batteryless reader. However, both methods need physical constraints because the stacking only works in specific orientations. The large footprint and the requirement of physical contact also discourage embedded and wearable applications. In all, they are not as easy to use as those small contactless NFC tags. So in this presentation, we introduce a near-field identification method that supports contactless pair identification. It works in every orientation, and its footprint is as small as a fingertip, so they can better support embedded and wearable applications. The key component that makes such a mechanism work is a component called magnet-biased read switch. A reed switch is a contactless switch that can be triggered by a nearby magnetic field. The switch closed according to the magnetic field intensity, regardless the polarity. If we fix a magnet next to a terminal of a reed switch, it biases the reed switch into a normally on switch, which has the same function as a wire with a near zero ohm resistance. So, for an RFID tag, we can simply replace a part of the circuit with a normally on switch, and it still works as a normal tag. Now it's the fun part, symmetric magnetic field interaction. When two same polar magnets approach to each other, their magnetic field strength reduced equally. Then the magnetic field interaction turns both switches off at the same time for pair identification that trigger a correlated state change without any physical contact and orientation alignment. To realize this, the first thing we need to know is where to place the magnet. The switch sensing volume looks like this. Placing a magnet in two distances will change its state. First, a magnet turns a switch off in D off. Then, a magnet turns a switch on in D on. The magnet should be placed within D on. Two explorative studies were conducted to understand the design parameters. In study 1, we tested 4 sizes of magnets and 2 types of reed switch, a larger one and a smaller one. We fixed them on a slider and checked the internal validity by measuring the D on and D off in a 1 millimeter step for 20 times. And both poles of each magnet were tested, and the measurement took about 1 hour. The result showed that reed switch readings are very stable, as the standard deviation of all repeated measurement is 0. Also, we learned that a larger magnet has a larger D on, and the polarity doesn't matter. In study 2, we use the strongest 2 magnets and test only one polarity. We test the external validity by sampling 2 switches in both types and measured their D on for 10 times. The measurement took about 4 hours. Results shows that both types of reed switch has a good external validity, as the standard deviation of D on are all about 1.5 millimeter. The smaller reed switch is significantly more sensitive than the larger one. Therefore, we come up with the basic module design. The larger switch and the strongest magnet was used. The distance between them is set 1 millimeter smaller than the D on, which is 15 millimeter. And we think such a gap distance can be repurposed for designing a finger stole, which allows a user to wear it on the fingertip. The finger stole allows the system to identify which finger it is. Smaller magnet and switch are also chosen for miniaturization. Moreover, since we use magnet, force feedback is a native feature. The user can feel a repulsive magnetic force feedback during the pair identification, and such a haptic landmark supports eyes-free interaction. And I actually have the module with me. Yeah, so later after the talk, you can feel the haptic feedback and to feel what kind of haptic feedback it is. So far, we have enabled embedded and wearable uses like NFC tags. Basic modules can be embedded in the everyday objects, so their aesthetics would not be compromised. Wearable modules further allow for touch interactions. Here's a smart showroom deploy a single UHF reader and our modules. So the users from different nationality can touch each other's finger like a movie E.T. to greet in each other's language. And the object knows who is touching it. So touch and tangible interaction are both possible in this setting.
Place an item here to order it.
Audio-visual feedback can be provided.
Brown mug. Yellow mug. Thank you for ordering.
Most importantly, in this example, only one reader was used for tracking all the near-field identification in a 30 square meter room. Performance evaluation. We evaluate the reliability by 3 measurements with 2 modules placed on a slider. 2 distances were obtained from each measurement. D1, where one of the switches is closed. D2, where both switches are closed. A small difference between D1 and D2 means a reliable pair identification mechanism. In the first study, we picked up 4 switches of the same D-on for measurement. They share the same 2 magnets of the similar strength, which is pre-measured. All 6 combinations were measured on the 1D slider in 20 iterations, and the measurement took 6 hours. The results show that in every combination, the mean differences between D1 and D2 are just about 1 millimeter. There's also no significance in distance with time. So it shows a good reliability when the modules are aligned. What if the 2 modules are not aligned? In the second study, we tested 2 switches with an offset Y and changed the orientation theta into 11 angles. 3 trials were taken in each angle until D2 cannot be measured anymore at an offset Y. A measurement took about 4 hours. The results indicate a sensing volume because the magnetic field interaction is symmetric. The results show that when the module is not tilted, the tracking is reliable in the volume. When the module is tilted with plus minus 45 degrees, the tracking is still in a reasonable performance, showing that it is capable of handling input from various angles. Will the performance change with time? Study 3 uses 10 modules. Each of them were calibrated with its individual D-on. We measured the 5 combinations in 3 trials for every 12 hours in 4 days. The results show that the tracking performance is stable with time, is unlikely to change. However, the different magnets result in different D-on. Because we are using different magnets. Despite that, the calibration has been conducted. So it informed that for further optimization, the strength of magnets should be also considered and examined before use. What can we do further? One can do is to add a button to the module. It adds an extra state of input and still keep it batteryless. Another thing we can do is to use the power harness from the tag to power up an LED. So it can provide visual feedback to other users in the surrounding. One of the obvious limitations of the normally on module is the scalability. When the number of tags increases, the idle modules generate lots of tag reads, which slow the system down. For instance, for 50 tags, the system has a performance of 25 frames per second, but for 200 tags, it dropped to 6 frames per second. Well, here's a solution. Using a normally off module can solve the problem. The normally off module places a magnet in different orientation, but the module size is the same. When the 2 modules attract to each other, both modules' magnetic strength increase equally because of the symmetric magnetic interaction, and turn on the modules at the same time for pair identification. In this way, no tag read is generated during the idle state. So the system does not slow down when the tag number increases, so you can deploy thousands and even 10,000s of the tag in one room. However, the normally off module only work in one direction. Make it harder to use than a normally on because the two modules need to attract each other. Okay, designers should keep this in mind. Future work can consider using a grid of biased reed switch for micro-localization in which a single magnet could bias all the switches. In this setting, gestural input between the two modules is possible. RFIMatch systems share the same operational limits with the related work. It can only resolve one pair at a time and cannot work well with metal. Localizing the tag could further make simultaneous interaction possible. The wearability of the fingerstyle can be improved by better manufacturing process using soft, flexible, and water-resistant materials. Please check our paper for a comprehensive discussion. Conclusion, RFIMatch is a distributed batteryless near-field identification system that eliminates the requirement of physical contact and alignment, minimizes the marker footprint, provides haptic feedback, and therefore enables embedded and wearable application in a scalable deployment. Thank you for your attention. I'm happy to take all the questions.
So we have time for one quick question. Dan.
Hi, Dan Ashbrook, University of Copenhagen.
Hi.
I'm curious about the size constraints of this. So you experimented with
Yes.
RFID sizes and so on.
Yes.
Can you coil up the antennas or do something to make these things a smaller size?
Yes, that's a great question. Thanks. The size constraint, the size of the tag mainly depends on the size of the antenna, right, because the antenna occupies a huge space of an RFID tag. So what we can do is to choose a smaller tag so that the tag size can be reduced. And one of the possible alternatives for the wearable form factor is that we can repurpose our skin as antennas, just as those examples demonstrate by Lee and his colleague in paper ID. Yeah, so that a wearable device doesn't need to embed with the antenna, and that can make the device much smaller. Okay.
Thanks.
You're welcome.
All right, let's give Rong-Hao another round of applause. Good chance.